This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
For the entropy following the particle of entropy, or following the mass as well, it's the same thing, d rho dt plus u dot grad u d rho d dxk and d rho, or rho u dot grad rho. So this is du dt, which is this du dt plus u dot grad of each component of u. And so this left-hand side is simply d dt following a particle. And then if I multiply this left-hand side by the whole equation by delta v, I have rho delta v du dt is minus grad p delta v plus rho f. And that is a statement of the mass times the acceleration. Rho dv is a small element of mass dm. And so this is the acceleration following that mass, following the mass itself, which is fixed as the particle. And then this is the pressure force acting, and this is the body force acting. So this is just Newton's law, and many people begin by writing that down rather than doing what I did. And now I wanted to say something here for you, because u dot grad u introduces spatial derivatives, or spatial gradients in the velocity u, and leads, one thinks naturally, to the possibility that it could be rewritten in a form which contains the curl of u, which is also some derivatives of the velocity field. But the curl of u has a specific definition. It's called the vorticity. Omega is the curl of u, and omega is by definition the vorticity. So, and the vector identity, which you should sit on your tail and actually work out as an identity, is that u dot grad u, or uk d dxk of ui, is equal to omega cross u, which is epsilon ijk omega j uk, omega I uj, I mean. Yes, for the kth component. And this is the gradient of a half u squared. All right, now we're going to use that now. But I want to say a little bit about the physical interpretation of the vorticity. So now, here's an equation much like Gauss's theorem, called Stokes' theorem, which relates the path integral of a vector around a closed loop, u dot dr around a closed loop, is equal to the curl of u dot n, where n is normal, is the vector normal to the loop, times the area. So this is omega, so we're going to take the normal component of omega dot ds. And here's something that I'm going to say and prove for you, that omega is a measure of spinning motion or rotation of a small sphere. So, for example, if we took a small sphere and we go around the circumference of that sphere, and we say u theta is the average tangential velocity, so it's u dot dr divided by the radius, so it's an average by the circumference. So it's the average velocity u theta by the distance that you go around this circle, which is 2 pi r. And that is the average value of the vorticity in the normal direction multiplied by the area, and the area of this little circle is pi r squared.
Sorry, Gary, along the closed curve, is dr then the tangent?
No. Dr is, of course, the tangent along the path. So here's my little sphere, and here is delta r. Here is the vector r. Here is r plus delta r. And delta r is this little change along the path.
dr is tangent to the path.
Yes,
Yeah.
so dr's along the path, and this is the vector u,
Yeah.
and u theta is the component in this direction. And so I'm going to sum that up, and I'm going to find an average value. So my integral of u dot dr will be simply the average value of u theta times the length, by definition. That's what I mean. So u theta is the average value around the loop by 2 pi r. And you can see that what is the average vorticity? It's, so I divide the left-hand side by pi r squared, and I get 2 u theta over r. But that's the angular velocity, twice the angular velocity, the average angular velocity of this sphere. So that's a very important idea. So here's the next statement that I have. Suppose you suddenly froze a spherical particle. The question is, would it rotate? So if you suddenly froze it, and it's spherical, you would conserve its angular momentum. No torque is acted. If it was an inviscid fluid, no torque would act. It's a sphere. And the only forces that act on a sphere are the pressure, and that acts normally. So you couldn't change the momentum. And if you froze it very quickly, you wouldn't change its angular momentum. And so, if you suddenly froze a particle, it would rotate if there's vorticity in the fluid. It would have angular momentum. For a spherical particle, if it has 0 angular momentum, then it cannot acquire angular momentum in a non-viscous fluid because the forces are normal to the surface of the sphere. And that is why you've been sitting here dutifully thinking about irrotational flow. And what is irrotational flow is simply a flow in which omega, the vorticity, is identically 0. Omega equals 0 is irrotational motion. So the Euler equation, I can replace that u dot grad u by omega cross u plus the gradient of a half u squared. So the Euler equation becomes very simple. It's du dt plus omega cross u plus the gradient of a half u squared is equal to minus the gradient of the pressure divided by the density plus the force per unit mass. So that is the Euler equation for inviscid flow. And it's terribly important. And if F is a conservative force, it can be written as minus the gradient of a potential. We saw that. Okay, so now I want to tell you about the Bernoulli equation. So I'm going to, oh God. So let's go back here to, there's the Euler equation. That's always true for inviscid, non-heat conducting fluid.
Does Stokes' theorem depend on it being a conservative field?
Stokes' theorem, no. Stokes' theorem is a theorem of mathematics in the same way Gauss's theorem is a theorem of mathematics. It's a statement that the integral around a loop of A dot dr is equal to the integral over a surface of the curl of A dot n ds. That's always true. That's Stokes' theorem, and it comes about for the same reason as Gauss's theorem. Namely, if I work out this little local thing, I can work out what this is around a square, and then I add up all the squares, and all of the lines going up are cancelled by lines going down. So they cancel, and so I only get, finally, the integral around the outside loop. And it's the integral around the outside loop, which is the sum of all of the curls of U over each little area, same as Gauss's theorem. All right, so now let's look at this equation, this Euler equation, which I've just written down, in some special cases. Let's suppose the flow is steady. We're going to do the simplest case first. The flow is steady, it's incompressible, meaning that the density is constant, and we're going to suppose that it's irrotational. In other words, omega is equal to 0. What would I get? Well, if rho is constant, d dt is equal to 0 because it's steady, and omega equals 0, and the stresses are 0, and mu and k, the thermal conductivity, are all 0, then this equation, this one, this term's gone, I've only got this term, and this last term, so they're all gradients, so I can put them all inside the gradient. And I've got the gradient of P over rho plus a half U squared plus this potential energy equals 0. And it follows, if the gradient is 0, I can form the dot product with any dr, any arbitrary dr, and I've got the change in this quantity inside. And so that quantity inside, the change has to be 0. So that quantity inside has to be a constant, same constant everywhere. So so many problems can be solved like that. Well, you just write down, and this is called the Bernoulli equation, and it's the same constant everywhere. Now let's relax some of these conditions. Suppose it's unsteady and it's incompressible, but it's irrotational motion. So rho's constant and rho's constant. So d dt is not 0, but it's irrotational. So omega is equal to the curl of U, which is equal to 0. But if the omega is equal to the curl of U is equal to 0, then you can prove mathematically that U can be, it's necessary and sufficient for U to be the gradient of a potential. It's obviously sufficient because the curl of the gradient is obviously 0. But proving that it's necessary is a little more mathematical. So we notice that if we also had rho's equal to constant, the divergence of U equals 0 in incompressible flow, it would mean that the divergence of the gradient of phi is equal to 0, or the del squared phi is equal to 0, which is what you've done in potential flow. But notice that in this case I can again integrate my, I've got a bunch of gradients now for my Euler equation, but I've got a new term. I've got the gradient of d phi dt, that's the du dt term, plus the gradient, plus a half U squared plus P over rho plus the potential energy equals 0. So that has to be 0, so I can form the dot product with any dot dr and get the change of this quantity inside. And so what satisfies this equation is obviously that this left-hand side is a function of time. And that is the Bernoulli equation in an unsteady flow that's incompressible and it's irrotational. And often this function of time can be put equal to something at infinity, where at infinity the velocity may be 0. The potential energy is frequently not very different, or we can change it and put the potential energy inside with the pressure. And then you get d phi dt plus a half u squared plus p over rho plus phi, and it's often equal to p infinity over rho. And so I put that, it's often p infinity over rho. So now, a very good example of this is cavitation. Let's suppose I had a bubble in the flow and it were oscillating. What would happen? It would radiate sound in the far field, but if it were incompressible, then it would cause a fluctuation in the pressure everywhere. And one of the lovely problems I got involved in was the Lysart Enterprise. And I was at Adelaide, and I was contacted through the chairman of the Australian Shipbuilding Board, and he said, we've built a ship called the Lysart Enterprise, and the customer won't take delivery of the ship. And I said, why not? And they said, well, they won't take delivery of the ship because the vibration at the stern of the ship is enormous and much larger than anybody predicted. And so he said, I'd like you to go and find out why. So the ship was tied up at the dock at Newcastle, and I flew over there and got on board, and I had with me an accelerometer. And I can tell you that the way the ship worked was that they changed the thrust of the screw by changing the pitch of the screw. So the pitch of the screw, it was a multi-element screw, and they just changed the pitch. And so we took the ship to sea, and I had a loud hailer to the bridge, and I asked the captain to give me increments in pitch as we sailed off the coast of Newcastle. And I can tell you that suddenly, at some particular pitch, the vibration was enormous. And I looked at the accelerometer, and the instantaneous peak acceleration exceeded g. So what would that mean? That would mean, and it was basically at 10 hertz. So, and I said, well, what's at 10 hertz? And the 10 hertz is the blade passing frequency. But the acceleration was so large that it was such that instantaneously my feet left the deck. It exceeded g. So in cycle, most of the cycle, of course, I was firmly attached to the deck. But because the acceleration was so high, I instantaneously left the deck. How could it happen? Well, I immediately thought of this equation. You tell me what happened. You're the consultant. I was your age when I was doing this. What happened? Somebody here must have some idea. Not a soul? None of you can tell me what happened? Not one? Won't matter if you get the wrong answer. What happened? What do you think happened?
Is it because it wasn't rotational?
No. Or that's possible, but this equation wouldn't apply if it were irrotational. If it were not. This is for omega equal to 0. So what happened? Well, here's what I thought happened. Here's the screw. Here's the aft end of the ship. And I'm standing here. So what do you think happened? Well, at some angle, at some pitch angle, presumably the flow around on this propeller disc caused the velocity would have been so high that the pressure went below boiling. Now what would happen? You'd get a big bubble. You'd form a bubble of vapor. Now what would happen? What would happen next?
It will hit the blade.
Beg your pardon?
It will hit the blade.
The bubble would be on the blade.
Yeah.
The bubble would be on the blade because locally the velocity was so high because the angle of attack was so high. You got locally a low pressure and it boiled. The water formed a bubble. Now what would happen next? It's on the blade. What? Erosion? Well, it might erode the blade over time. Why was the acceleration so high on the ship? Come on. The bubble is there, and then the propeller moves into deeper water, and the pressure goes up, and the bubble collapses. Now what happened? Way away, so you have a bubble here. What about if you were over here? What would you see? Would the pressure go up and down? And if so, why? What if I had a spherical bubble here? And suppose I had a spherical bubble and I oscillated it. I managed to oscillate this bubble at its resonant frequency. I could, if it was filled with air, I could make it resonate. What would happen? What would the pressure be? How would I find out what the pressure is over here? You no idea? Good God. You'd write down the potential. There has to be a velocity potential here, which would be some source over 4 pi r. Why? Because you'd have to keep symmetry. And if you oscillated it, I'd have to find the gradient of it. d phi dr would give me 1 upon r squared. And so it would be the same all the way around the sphere. And the velocity would be oscillating, which is what I would have expected. But it would be the same all the way around the sphere. So now I put a bubble on my blade here, and what will happen? I'll produce a fluctuation in the far field of the velocity and the pressure. But it'll be uniform over a big area. So what I expected to have happen is that all the way under here, the pressure would fluctuate. But that's a big area. And when you integrate the pressure over a big area, you get a very large force. And if it corresponds with a resonant mode of the ship, you'll drive it crazy. And it'll oscillate. And you'll get huge oscillations on the aft end of the ship. And that's what happened. That's exactly what happened. And I proved it by getting the captain to drill a hole in there. And I measured the pressure, and I could see what was going on. So now, how would you fix it? How would you fix it? What would you recommend? Your job, you're in charge, you're the consultant. What are you going to recommend? How do they fix it? Nobody has any idea? What if the reason this happened is that the flow through here was not what they thought it was, and the angle of attack around that blade was much higher than they thought it was? How would you reduce the angle of attack? You'd get more flow through the propeller disc area. you try and get more flow. How would you do that? Nobody, any idea? How would you do it? You might try and put some sort of devices on the hull that would cause that flow as it's coming in not to separate. Because you think that probably what happened is that the flow around the hull was not very good and it separated sooner than they thought it was going to separate. And you had a low velocity there, and so the blade cavitated. So you do that. And now, where would you do that? Would you require them to go all the way overseas to design this thing to change the flow through the propeller disc? Or would you do it in air? The answer is you'd do it in air. And you'd turn the ship upside down, and you'd put it on the floor of a wind tunnel, and you'd put some devices like that and try and change the flow through the propeller disc, which you could measure. And provided the Mach number was very small, the fluid, air, looks like water. And I could find out what the velocity was. So that's what happened. All right. Oh, what happened here?
Second window.
Oh, God. Here we are. I'm sorry. I think I'm nearly... hit that one?
Yes. Oh, where is it? Click it again. Yes.
Yes, thank you. You've done it. Sorry. All right, so that's where we were. And I did the Bernoulli equation for you. Unsteady, incompressible flow, and cavitation, and this dphi dt term. And now let's do compressible, irrotational, steady flow. So rho is now not equal to 0. d dt is equal to 0 because it's steady. Omega is equal to 0 because it's irrotational. And tau and q are 0, which means that S is constant, as we've seen before, and there are no shocks. So for the same S everywhere, oh God. We know the thermodynamic identity that TdS is dH minus dP over rho. And this delta H is the gradient of H dot dr, where dr is some small displacement, arbitrary displacement, minus the gradient of P over rho dot dr. So that if S is equal to 0, this left-hand side is equal to 0. And then I can put inside here the gradient of H minus grad P over rho dot dr. So I can replace in my Euler equation the gradient of P over rho by the gradient of H. And that is why the enthalpy plays such a central role. So that's telling me that the gradient of H plus a half U squared plus phi equals 0. And that says that H, the enthalpy, plus a half U squared plus phi is equal to a constant. Now, let us look for the minute at rotational steady flow. And we're going to look at incompressible flow, and then compressible flow. So now the simple case that we've got is that it's steady, d dt is equal to 0, but omega is not equal to 0. The stress and the heat flux vector are all 0. So S is constant. So now we're going to go back here to my Euler equation. So there it is there. And I'm saying it's steady, and initially, initially it's rotational, so omega is not 0. All right. So now let's suppose I do something. I take u dot of that times that equation. So I have u dot of omega cross u plus u dot of the gradient of p over rho plus a half u squared plus phi equals 0. So this is the incompressible case. So that says, now what if that u is simply some delta r divided by delta t, but delta r is in the direction of u. So by definition, u is the displacement delta r divided by delta t. And but this term, u dot omega cross u, is well known to all of you, I'm sure, as being 0 because it's a matrix with 2 rows the same. So you could work that out. If you have 2 rows of a matrix, and this is this product is identically 0 if you have 2 rows that are the same. So that says that the gradient of p over rho plus a half u squared plus phi dot dr is equal to 0. But if delta r is u delta t, is the distance along a streamline, then it says that this quantity here, because this term now can't be 0 in general, so for this to be equal to 0, it says that this change in this quantity here, which can be written as the gradient of this quantity dot dr, is equal to 0 on dr, meaning that this delta h, if that's equal to 0, it means that this delta h is equal to 0 along that path. And that means that this p over rho plus a half u squared plus phi is constant, but in this case, so this is omega not equal to 0. This is constant along streamlines, but it's a different constant for different streamlines. And that's terribly significant and important.
So are these following, for instance, the path of the particle?
Yes, exactly. Following the path of a particle. And in steady flow, that's a streamline, in steady flow. So for incompressible flow, it says that p over rho plus a half u squared plus phi is constant along streamline, and it's a different constant for different streamlines. Terribly important in rotating machinery, for example. And the same thing for compressible flow. You can do exactly the same. You can replace, so long as the entropy is not changing along a streamline, then it'll become h plus a half u squared is phi. It's constant along streamlines in compressible flow. So that's very evocative. It says, well, it seems as though that's a statement from the energy equation. So let's look at the energy equation and compare the energy equation and the Bernoulli equation. So let's suppose I had a stream tube here and I go from 1 to 2 and it's steady flow. Then the energy equation reduces to something simple. It says that the integral over this volume, including the surfaces 1 and 2, and these boundaries here of the stream tube, the integral of rho u dot n h plus a half u squared plus phi is ds is equal to how much heat is supplied minus how much work is done by the fluid inside plus the viscous work that's done on the surface, tau ki ui nk ds. So if this is a stream tube, even if the fluid, even if it's a solid stream tube, there's no viscous work done on this boundary. Why? because the velocity is identically zero. So the viscous forces on that surface are identically zero. Now, on this end, it could be that ddx is identically zero at both ends here. There's no change in x, and so viscous stresses don't do it. There is no viscous stress in that normal direction. So,
Do you tend to think of this stream tube as the evolution of a particle in time, or at a fixed spot in time is the stream, fixed slice in time?
I can think of it both ways. It's the same thing as a particle that moves from 1 to 2, or I can think of it as the path within which the fluid is flowing. So either, but it's a stream tube and it's steady flow. I was at pains to tell you it's steady flow because I left out the first term here, which is the rate of change of energy within the volume. That's zero. Now, equally, the mass equation is that the net mass flux out of this control volume is zero. And so because there's no normal velocity to this through this surface, this is a stream surface here, there's no normal velocity to it. There's only a normal velocity at 2 and at 1. And so rho u dot n ds means that in this case n is in the minus direction, and but rho 1 u1 a1 will be the same here as it is here. This will be rho 2 u2 a2, and the statement of this mass flux is that this is minus m1 and this is plus m2 is equal to 0, or that m is a constant. M is rho 1 u1 a1 and rho 2 u2 a2. So in the special case where there's no heat supplied and no external work done, and the shear stresses are 0, then this equation reduces to something extremely simple. M dot H2 plus a half U2 squared plus Phi2 minus M dot H1 plus a half U1 squared Phi1 equals 0. And that is that H plus a half U squared plus Phi is constant along a streamline. And that's the same as the Bernoulli equation. But we're going to use that a great deal. And supposing now you were doing some sort of a problem and you had to work out whether, so you knew U1, U2, U1 and rho 1 and A1, and you know A2 for this stream tube, and you know the potential energy, how high it is above the ground, for example, at 1, and how high it is above the ground at 2, and you know what the pressure is at P1. What is the solution for rho 2, U2, and P2? Can I solve it? Can I solve the problem? So how would I do it? Well, I have an equation of state for this fluid. H is H of S and P. And I know from that and from the thermodynamic identity that the temperature I can find at every point. It's just dH ds at constant pressure. And I can find the density, which is the specific volume, which is dH dP at constant S. And why do I say that? Because TdS is dH minus dP over rho, or minus V dP, right? So if ds is equal to 0, it says that dH dP at fixed S is equal to 1 minus 1, is equal to 1 over rho. Sorry, it's minus. No, it's plus 1 over rho. dH ds, sorry, no, it's not, it's minus. At constant S, this is 0. It says that dH dP is equal to 1 over rho. Well, that's correct. And equally, that dH ds, dH ds at fixed pressure will be the temperature T. dH ds at fixed pressure, this is 0, will be T. So that's why it's a canonical equation of state. Everything follows from it. So there it is. I've just worked it out for you again there. So I could write down rho as a function of S and P. So now how would I solve the problem that I just posed? Well, I would have to choose initially an S1, because I don't know what S1 is. And that when I choose an S1 and I know P1, I would get an H1, and I'd get a rho 1 from this expression here, and I'd have to keep iterating S1 until I got the right rho 1. And now I would want to solve for U2 and P2, and I can only do it if S2 is equal to S1. If S2 is equal to S1, then I can write that rho 2 U2 A2 is rho 1 U1 A1. That I know from conservation of mass. And conservation of energy is H2 plus a half U2 squared plus Phi2 is equal to H1 plus a half U1 squared plus Phi1. So what I would do is I would choose a U2 here, or here, and I know rho 1, U1, and A1, and that would lead me to a rho 2 here, and it would lead me to an H2 here, and an H2 and an S1 would lead me to a P2, and for S2 is equal to S1. And I then have to solve for the density, and I'd keep iterating on U2 until I got the right self-consistent rho 2 here, which I got from conservation of mass. So I would iterate to find U2. So now I want to talk about, I want to use this result for what are called static and reservoir conditions in supersonic flow. So the static conditions are P, rho, and T, and they are the local values of P, rho, and T that would be measured if you were moving with the fluid. So if you moved along with the fluid and you had some technique by which you could determine the pressure, you would determine the static pressure. If you had some technique for determining the temperature as you were moving with the fluid, some laser, for example, to determine molecular spectra from which you could find the temperature, you would be determining the local values of the temperature. So P, rho, and T are the local values that would be measured if you were moving with the fluid. Okay, so now what do I mean by static and reservoir conditions and total conditions and so on, because that becomes very important. Yes?
So if you move in the frame of the reference of the particle,
yes.
you would measure a different temperature to if you just probe.
Oh, if you stuck a probe in there, then the probe would have an effect. And who knows what the probe would do. So measuring, for example, the static pressure is not easy. Typically, it's done with a static pressure probe that has holes around the circumference, some distance from the leading edge, and it takes the average pressure at these holes. And you hope that that's the pressure you would measure if you were moving with the fluid. And it's very close. But, so let me say a bit more about the total, what I mean by the reservoir conditions and what I mean by total conditions, because that's going to be very important. So let's suppose that I have a moving fluid here that's moving with a velocity u, and it has an enthalpy h when I'm down here. But I'm supposing that it's come from a very large, very, very large area upstream. If it's coming from a very large area upstream, the fluid's hardly moving. But then it converges and it starts to move rapidly. All right, so when it's right upstream up here, if this is a very large area, the velocity is almost zero. And so this I'm going to call the reservoir condition, where the velocity is literally zero. So this, but my conservation in steady flow says that rho u dot n h plus a half u squared ds is zero. But this, right up here, ds is much bigger than here, and because of this conservation of mass, I have negligible velocity up here. So, but down here, let's supposing I had uniform flow over this area, then it would be h plus a half u squared would be this quantity inside here. And right up here, it would be h naught. Now that is just the same as what I had before for my equation. I had here m dot h plus a half u squared plus the potential energy, and let's suppose it's horizontal, so that's not changing. H plus a half u squared minus m dot, or in other words, I can cancel the m dot, and h plus a half u squared, and if there's no potential energy or that's not significant, then I get, and it's typically not because the mass is very small for air, then I get h plus a half u squared is h naught, where h naught is the stagnation, or sometimes called the reservoir enthalpy. So now let's suppose that I go on from there and I talk about a second reservoir. So I speed the flow up, and now I have an expanded area, and it's going very, very slowly again down here. So I have now a total enthalpy h naught prime and a total enthalpy h naught. It must be true if the velocity is negligible. The energy equation demands that h naught is equal to h naught prime. That is why the enthalpy is so important in compressible flow. It's because the total enthalpy will be conserved, or that's the reservoir enthalpy will be the same. We're going to, oh God.
Can you go to LMS? Is it there? This one.
Ah, thank you. Thank you. Okay, so now, and what is terribly important is that it's only for a perfect gas that this implies that T naught prime is equal to T naught. It's only for a perfect gas. Why? Because for a perfect gas, the enthalpy is CPT. So for a perfect gas, the specific heat is constant, and it's equal to the Cp, the constant at... so it implies that T naught prime is equal to T naught if this is true, but that's only for a perfect gas. Thermodynamics requires that the entropy here is higher than the entropy here, always. The total entropy, the reservoir entropy. Now, why is that? So this is one of the reasons why we spend as much time as we did proving these thermodynamic principles. So I'm going to do something simple for you. I'm just going to remind you that here's a cycle, and I drew this cycle to you before, and I said that if it was a reversible cycle, then I could replace this cycle by a bunch of infinitesimal cycles that were all Carnot cycles, and I'd accept heat dq2 here at T2, and I'd reject heat dq1 at T1 here, and I'd have all of these infinitesimal cycles adding up to the total cycle. And so the ratio of the absolute values of dq2 to dq1 is T2 over T1 for a Carnot cycle. And if I make heat supplied positive and heat rejected negative, then this becomes the magnitude of this divided by T2 is the magnitude of this divided by T1. Or if I put these signs in, I have dq1 over T1 plus dq2 over T2 equal to 0. And that says that if I go around this loop and I do it all reversibly, if this is a reversible loop, then I get 0. And now what I'm going to do is I'm going to say, well, let's suppose this cycle is not a reversible cycle. But I'm going to suppose that I supply the dqi at Ti supplied to this cycle A by a reversible Carnot cycle between T0 and Ti. So that this ratio of the absolute values of the heat supplied from the reservoir T0 to the ith component of the heat that has to be supplied is the ratio of these temperatures, absolute temperatures, T0 over Ti. So this Carnot cycle is supplied heat dq0i at T0 and rejects heat dqi at Ti, and the dqi is the heat supplied at Ti to this cycle.
This is reversible process?
No. What I'm going to say now is that because all of the heat to the cycle is now being supplied at one temperature T0, Kelvin's statement of the second law says that it's not possible to get work out of this cycle. And it's obviously, PV diagram is obviously generating work. It's not possible to get work out of this cycle if the only effect is heat from a single source, supplying heat from a single source. So heat supplied and rejected to the cycle A is therefore provided by n reversible Carnot cycles, and the total heat supplied to the whole system, which cycles once, is dq0i. And that's going to be T0 times dq, the sum of dqi over Ti. And Kelvin's statement says that because you're doing work, you can't get work from a single source of heat at one temperature. And that's all of the other sources of heat and sinks of heat come from the Carnot cycles, and they're balanced exactly. So this thing has to be less than 0, and it must be less than 0 since the net system must only reject heat and not supply heat at T0. And that's Kelvin's statement of the second law. And it's clear that if I reversed the main cycle and reversed all the other cycles, then if I reverse everything, then this thing has to be identically 0. So that the sum of dqi over Ti is equal to 0, or for any cycle, the sum of dq over T has got to be less than 0 for any cycle, and if it's a reversible cycle, the integral around the loop of dq over T has got to be equal to 0. And that was so basic because that enables you to define dq reversible. So let's do that, remind ourselves that leads to the idea of the entropy. The entropy at B minus the entropy at A is the integral from A to B of dq reversible over T, because the integral from A to B, so if I go from A to B like this path, and then come back to here, because the integral around the whole loop has to be 0, it has to mean that the integral on this path is the same as the integral on this path. And if that's true for a reversible process, then that leads to the definition of entropy. So now I want to prove to you, and I didn't really before, that SB minus SA is always greater than or equal to the integral from A